Okay, so this is my first time trying a double screen record like this, so let's hope it goes alright. So I have my notes here on the left, and then my Desmos on the right, so hopefully this displays like I want it to. So we're going to talk about optimization. Now optimization is a pretty hefty topic, which is why I spent 2 days on it. In order to do this correctly, you're going to want a pencil or pen and a highlighter. So I'm going to grab, I had a pen, but I'm going to swap it out for a pencil just so that I can erase any mistakes if I make them. Okay, so the goal of an optimization problem is to find an optimal solution to a given problem. And by problem, I don't mean stuff like solve for x at this point. I mean stuff like you have a decision to make. What's the best decision? Or you have this much material. What's the best way to use it? Like, we're talking actual situations with some context. So you're going to be given two what we call constraints. And constraints are caused by having a limit on the amount of something that you have. And you'll also be given an objective. In all of these examples, that objective is going to be money. So you're going to want to make the most money, and in order to do that, you need to optimize the profit. So the objective is going to be what you want to optimize. Now, the optimal solution will be one of the what we call corner points of the feasible region. Now, feasible region was a term that we introduced in the last video, and the feasible region is simply the solution set of a system of inequalities. Now, because we're dealing with practical problems, we're not going to be dealing with negatives anymore. So we're not going to be dealing with a full coordinate plane anymore. We're just going to be focusing on the first quadrant. And I'm actually going to focus my Desmos on just the first quadrant to reflect this. Now, what we're going to be looking for is a system of inequalities that kind of looks like this. All right? Kind of looks like this. And they're both shaded downwards. So the feasible region is going to be right here, where the two shaded regions overlap. And the corner points, let me see if I can improve the quality of this part. Okay, so the corner points are going to be the points on the boundaries of this double shaded area, of this feasible region. So these are the corner points in this particular illustration. So, we are now going to apply this to a problem. So, when I do a word problem, the first thing that I do is I look at the end and I see what am I trying to do? Optimize the profit. Now, I underline key information pertaining to the goal of the problem. So, optimize the profit, I highlighted that because I want it to stick out. This is the most important part of the problem. This is the goal. So in order to optimize the profit, I'm going to need a bunch of information. So a farmer has a field of 70 acres. And note how I'm not just underlining the word 70 acres. I'm underlining a field of 70 acres because that shows that 70 acres is the amount of space in a field. It's not just a random 70 acres. And so he plants potatoes and corn. The seed for potatoes costs $20 an acre to plant. Corn costs $60 an acre to plant. The farmer has set aside $3,000 to spend on seed. Okay, so that's going to be a budget. That's important. That's a limit. That's a limiting factor. And the profit per acre of potatoes is $150, and the profit for corn is $50 an acre. Okay. So we have 6 pieces of key information, and this is what you're going to be given. You're going to be given 6 pieces of key information. Now the constraints, actually first thing that we need to identify is, well, we've done the key information. X and Y are the two things that we're profiting from. In this case, that's potatoes and corn. X is usually the one that's first mentioned in the problem, so that's going to be potatoes. And specifically, X is going to represent the number of acres of potatoes planted. Y is going to be the second one, which is corn. So, now we have to identify what the constraints are. And I we'll tell you right now, all of the constraints will be inequalities with less than or equal to's. So, the two constraint equations will have some information on the left side and a total on the right side. That total is the total amount of something, the total finite amount of something that you have a limited amount of. So, for example, you have a limited amount of money to spend. So that's going to be 3,000 on the right side of the constraint. And this is money spent. So whatever we put over here, the amount of money that the farmer spends has to be less than or equal to $3,000 or else he goes over budget. The second constraint is space, which is 70 acres. So this is farmland, I guess we'll call it. Farmland, aka space, I guess. Like the amount of space that he has on the field. Farmland space. So everything in this first equation now has to deal with money spent in terms of potatoes and corn. So how much will you spend on potatoes and how much would you spend on corn? That's what goes in this equation here. And then in the second equation, and I know they're not equations, they're inequalities, but in the second inequality, we have everything to do with farmland space. Okay, so money spent. This one's the easier one, and this is how most of the constraint equations are going to go. The second one is kind of an oddball, I will say. This isn't a great example to start with, but the back example is much more like how I would normally give an optimization problem. So, the first equation is going to be very, very much like the equations that you're going to be making yourself. Okay? 3,000 is on the right, because it's the amount of money he has to spend. Now on the left, we're going to put the amount of money that you would spend on potatoes and follow that up with an X. So the potato cost is $20 per acre, so that's going to be $20 for every acre of potatoes. So 20 times the number of acres of potatoes is how much it's going to cost for all of the potatoes together. Then we're going to add that to the cost of corn, which is going to be $60 for every acre of corn. And that's our first constraint. Now, because X represents the number of potatoes and Y represents the number of corn, the second constraint does not follow this traditional logical reasoning. The second constraint is simply the amount of acres of potatoes plus the amount of acres of corn, and that has to be less than or equal to 70. So if X is the number of acres of potatoes and Y is the number of acres of corn, the total number of acres would be X plus Y. But we don't really know how many acres of potatoes are going to be planted and how many acres of corn are going to be planted, but we know that the total has to be less than or equal to 70. Otherwise, you're going to run out of space. So now the objective is the profit. So now we're going to take these two pieces of information, all right, $150 for every acre of potatoes and $50 for every acre of corn. That's the objective. And now we're going to make a table. So our table is going to have an X and a Y as the first two columns. And we're going to put our objective over here. Now, if it helps you to see what the objective is, you can put P equals beforehand to show that this is equal to the total profit. You get $150 for every acre of potatoes plus $50 for every acre of corn. That's your total profit. But don't put P equals in the third column, otherwise Desmos will break. Now this is where Desmos comes in, and this is why we're doing a double screen record. So I'm now going to type in my two constraint equations just like this. So now you can see that they're both kind of covering the whole thing, so I'm going to need to zoom out quite a bit. And you can see that we have this nice system of inequalities right here. So now, in accordance with the picture that we drew, or similar to the picture that we drew, we're going to find the three corner points that are touching the double shaded area. Now, when you click on this first line, you're going to be met with 3 points because there's a third one over here. The only 2 points that you want are the ones that are touching the double shaded area. So these are 2 of the corner points. The third one, you might think that is this one, but it's not. It's this one down here because this one is only touching the blue area and not the double shaded area. So we need the corner points on the whole feasible region, which is just the double shaded area. So we've got 1, 2, and 3. Now unfortunately these will not stay up. Yeah, these will not stay open for this next part, so you are going to have to kind of memorize them. But you can click on them and then click off again. Now on a third line, we're going to go to this plus button here and we're going to add a table. I'm going to get rid of the ones. We can just highlight this whole box and replace Y1 with just Y. And now for the third column, I'm going to put my objective, and I can do that by clicking to the right of Y here and adding 150x plus 50y. Alright, so now I have a three column table with that looks just like the 3 column table here. So now I'm going to click on my 3 corner points, and what's going to end up happening is when we input the coordinates of this corner point into my X and Y columns, it's going to spit out how much money I would make by planting this many potatoes and this much corn. Because remember, this is the objective, so this is the profit that we would make. So this is the profit that we would make from this particular configuration of potatoes and corn. Alright, the next one is 30 and 40, so 30 acres of potatoes and 40 acres of corn. That produces 6,500. And down here we have 70 and 0. So 70 acres of potatoes and 0 acres of corn. Alright, so that produces 10,500. So which one is the optimal solution? Well, first of all, let's copy our table here. So we've got 0 and 50. That's going to give me 2,500. Then 30 and 40. That's going to give me 6,500. And lastly, 70 and 0 is going to give me 10,500. Now this is in dollars, so this is $10,500 versus just 6,500 and 2,500, 2,500. So which one is going to make the most money? It's this one. So therefore the optimal decision is to plant 70 acres of potatoes, because X is 70, so we have 70 acres of potatoes to plant and no acres of corn, because corn just is not that profitable. So, in this particular situation at least. So, 70 acres, the optimal solution is to plant 70 acres of potatoes and no corn. Now, this is obviously there are more factors that go into farming. This is just a math problem that oversimplifies it a little bit. But with this oversimplification, the optimal solution to make the most money is to plant all potatoes and no corn. So let's flip to the back and do another problem. Okay, a manufacturer of ski clothing makes ski pants and ski jackets. Okay. The goal is to maximize the profit, as usual. So our key here is there are 60 minutes of sewing operator time and 48 minutes of cutter time available. It takes 8 minutes to sew 1 pair of ski pants, 4 minutes to sew 1 jacket, and cutters take 4 minutes on pants and 8 minutes on a jacket. The profit on a pair of ski pants is $2, and on a jacket it's $1.50. The two things that we're selling here are ski pants and jackets. So those are my X and Y. X is going to be the number of ski pants, Y is going to be the number of jackets. So now we have to identify the constraints. The two things that we have a limited amount of, the two things stopping us from producing an infinite amount of ski pants and jackets are the cutting and sewing time available. So my first constraint is just going to be on cutting time. It's just going to be on sewing time. And my second one is just going to be on cutting time. So the total amount of sewing time that we have available is 60 minutes. So that's going to be over here. And in cutting time, it's 48 minutes. So that's the hardest part, is identifying what are your totals. Total available sewing time is 60 minutes. Total available cutting time is 48 minutes. That's what goes on the right side of the constraint equations. So now for the left side. Everything over here has to do with sewing time, but it's the sewing time of ski pants and the sewing time of jackets. Okay, sewing time of ski pants is going to be 8 minutes for every ski pant, or every pair of ski pants, and 4 minutes for every jacket. And the cutting time is going to be 4 minutes for every pair of pants, and 8 minutes for every jacket. So these are our constraint equations. Our objective is the profit. So we make $2 for every pair of ski pants. This is the profit. And $1.50, actually I'm going to write it all the way out. We make $2 for every pair of ski pants and $1.50 for every jacket. So in my table, I'm going to write X, Y, and then $2 for every pair of ski pants plus $1.50 for every jacket. And now we go over to Desmos. So we've got 8x plus 4y is less than or equal to 60, and 4x plus 8y is less than or equal to 48. Okay, let's get a better view. We can press the home button to go back here, and this is perfect. Okay, so now we need the 3 corner points. We'll make a table here. Get rid of the ones. Put our objective. And now we enter the corner points. So the first one is up here, 0, 6. Second one is over here, 6, 3. And the third one, it looks like it's down here, but it's not. It's here, because we need it to be bordering the double shaded area. Alright? 7.5 and 0. So it's, now you can see that the blue dots, which, yeah, Y is blue in this case, are my 3 corner points. You can see that they illustrate the corner points perfectly. And now we can figure out what our optimal solution is. So let's copy the table down. So which one gives the most amount of profit? Well, it's the one with the biggest number in the third column, which is this one. It makes $16.50, whereas the others don't make that much. So the optimal solution is to produce this many ski pants and this many jackets. Oh, I did not mean to write X. Produce 6 ski pants and 3 jackets. There you go. That is how you do an optimization problem.